I will now continue class with the topic of substitution. So allow me to share my screen again. Okay, so you can see now substitution. Okay, this is the part wherein you may use power rule, or you can integrate your given function directly, because together with it you have already the derivative of such a function. So when we speak of substitution, we make sure that the derivative of a given function, which say u, when you differentiate it, that should be g prime of x dx if u is g of x. So if you intend to integrate, let's say, a function of u, which is a function of g of x, together with it, you should have the g prime of x dx. This particular process of integration allows you to integrate this given function of g of x, provided that the derivative of this function of g of x is with it or is multiplied to it. So as I have mentioned a few seconds ago, this will prove useful if you're using power rule or other techniques of integrations wherein it is required that the derivative of the function should be multiplied to it. You will understand better as we go along. So there's two ways that we can apply substitution. So it's either on the form u du, where u can only be integrated if its derivative is multiplied to it, or the u raised to n du, which is the one that I have mentioned regarding the use of the power formula. So these two patterns we will adhere to when we use the method of substitution, or we will follow. Now, if the g prime of x, which is the derivative of your f of g of x, is not complete based on a lacking constant, you need a constant to it, multiplied to it. So you may either multiply or divide by that particular constant. In the process of multiplying and dividing, we always modify our original integral by multiplying it by 1. Okay, we cannot just simply multiply by 2 and we don't do anything other than that multiplication by 2. You will know as I proceed here on the next slide. Now, so we go to the first example of substitution here. Interrupt me if you think I'm too fast or you cannot follow. You have here 5x cubed plus 1. It's placed in a parenthesis and it's being multiplied to 15x squared dx. Actually, you can have this answered by distributing. You can distribute 15x squared to this. That way, you will have corresponding two terms to process using power rule. So you just multiply 15x squared to this, and you will have 15x squared multiplied to 1. So you will just have to evaluate two integrals using power rule. In this case now, we will use the method of substitution. That way, you will not need to expand anymore. So we will not do this one, although you are allowed to do it. We will use substitution instead. So looking at 5x cubed plus 1, if you consider this as the u, so if you let 5x cubed plus 1 as the u, the derivative of this, which is the du, is, of course, 3 times 5, 15x squared. The derivative of 1 is 0 because it's a constant. So if you notice, the 15x squared class is already in here. You could see that it's already in here. So what you can do, you simply apply power rule to this quantity 5x cubed plus 1. So you can consider this one as u raised to n, and this entire thing here is your du. So this is the pattern that where we were going to use substitution. So if this is your u and this is the derivative of your u, then you are allowed to use power rule to this. So if you use power rule to this is your u, and the power rule says that it should be, if this is raised to 1, then that should be u squared, 1 plus 1 over 2 plus c. So what is the u? This is the u, 5x cubed plus 1. So you just simply raise the entire thing by 2 and divide it by 2, or multiply it by 1/2 plus c. So this is a shorter way of evaluating this integral without having to resort to expansion, wherein you need to multiply 15x squared to 5x cubed plus 1. Okay, so this is one pattern that was used here. You use power rule, okay, by identifying 5x cubed plus 1 as your u. Okay, now we go to number 2. You have 2 quantity x plus 3, or 2 times the quantity x plus 3 divided by the square root of x squared plus 6x. Now, this is really difficult in terms of division. You cannot divide, nor you cannot do expansion in here, because it will not simplify the problem for you. So what you can do, you have this complicated expression in the denominator. You can set this as your u, the x squared plus 6x. Meaning, class, this u that you have in the denominator is actually equivalent to u raised to negative 1/2. Why am I saying that? Because the square root here tells you that the exponent is 1/2. Since it's written in the denominator, then it's negative if you wish to write it in here. Now, if you have that in mind, if you have in mind that you will use power rule for this, then your u will be the x squared plus 6x expression. Now, check whether the thing that you see here in the numerator can represent the derivative of this u. So there's a need for you to differentiate. Now, when you differentiate, this will be 2x plus 6, right? Your answer is 2x plus 6 dx. That's the derivative. Now, you see here at 2 and 6, you can factor out 2 for that. So, it is now equivalent to, you can see here, if you factor out 2, you will have 2 times the quantity x plus 3. Now, with this as the derivative of your chosen u, you see that it's already here in the numerator. So meaning this entire expression here in the numerator will stand or will be the derivative of your u, which has the exponent of negative 1/2. So then we can say that we can use power rule to u raised to negative 1/2. If you use power rule, that would be u raised to 1/2 over 1/2. But what is u? Isn't it that u is x squared plus 6 as written here? So you copy that, x squared plus 6. But it has an exponent of 1/2. So that explains this square root sign or radical sign. This 2 that is multiplied to the square root of x squared plus 6x is actually the 1/2 here in the denominator. The 2 went up in the numerator. So this is the answer. Now, in these two scenarios, you use substitution. That way, you can apply power rule. So, you represented your u as a set of terms. So, your u is not just one function, but in here, it's x squared plus 6x. In here, it's 5x cubed plus 1. So, these are the two examples for substitution for this particular slide. Do you have any question here?
Miss, question.
Yes.
For the example number 1, Miss, din gan ihalin ang 1/2, Miss.
Ang 1/2 sa number 1. Isn't this your u? This is your u, right? And it's
Yes,
raised to 1, understood to 1. So if you use power rule, it would be u squared over 2. So the 1/2 here came from the over 2 here. Because your u is 5x cubed plus 1. It's squared, so you see here at 2. Do you get it?
Yes, Miss. Thank you.
Do you get it?
Yes, Miss.
Okay. So questions? Okay, so I will clear now my marking. So we go to the next slide. We have more here. This time, we will not limit yourselves to just the x and y variables, but we'll have here a trigonometric function. So this is your sine 10x dx with a constant of 10 here. Okay? This would be using substitution because the argument of the sine, what do I mean with the argument? The theta of the sine. The argument of your sine is 10x. It's not just sine x. So we can use the formula for the integral of sine u if the derivative of this u, which is 10x, is complete. So you can see here, u is equal to 10x because this is your sine u. What's the derivative of the 10x? It's 10 dx. So meaning the 10 that you see here, together with this dx, is actually the du. So you can now view this integral as sine u du. Now we have a formula for this. The integral of sine u du is negative cosine u. Let's see. So what is the u? You go back to this 10x. So negative cosine of 10x plus c. So you used here substitution because that theta is not just x but rather 10x. So the derivative of this 10x has to be multiplied to the sine function so that we can write its integral as dictated by the formula. So the formula is stating that the integral of sine u du is equal to negative cosine u. So how do you interpret this? This is the derivative of the u in here. Okay? It's not always x that you will have for the derivative or for the argument of any function whatsoever. It could be another function. And if that is the case, class, if the argument of a function is another function, that du of that argument should be complete. Okay? Now, we go to example number 4. Negative cosecant squared x over cotangent cube x. If you look at this, you always look for association, class. Is cotangent related to cosecant squared? Of course, the answer is yes, because we know that your cotangent function has the derivative cosecant squared x. So knowing that, seeing that these two has an association, one is the derivative of another, then you can let u as your cotangent x only. So this thing here in the denominator is comparable to u raised to n, where n here will be negative 3 because it's written in the denominator. Now, if you set the u as cotangent x, what is its derivative? It's negative cosecant squared x dx. So meaning, again, the entire expression here in the numerator is the du of the cotangent. So it's like writing it in this manner. Now, the integral of cotangent x raised to negative 3 times negative cosecant squared x dx. This is your u raised to n and this is your du. This entire expression is the du. So using substitution, you can now use power rule for the cotangent function. Now, if you use power rule, this would be, the answer actually is cotangent of x raised to negative 2 all over negative 2. That's power rule, right? With this one as the derivative of your u. Now, what is this? So you can simplify this further as negative 1/2. Then you have cotangent squared x here. Now, we place it in the denominator that makes the exponent positive. If you want to write the equivalent of 1 over cotangent, that would be this. So that is why you see there a negative 1/2 tangent squared x plus c. Do you follow? Can you follow samples 3 and 4? Or do you have any question? Normally, class, we apply really substitution in power rule or in other functions whose argument is another function. I think that would be illustrated for my on my next examples. But here, do you have any questions? Okay, so there's none. So I will clear my markings here and we'll proceed with the next slide. Okay. So this time, you have x squared times the quantity x cubed minus 1 raised to 4 dx. Whenever you see this class, it's really a big no-no to have x cubed plus 1 raised to 4 expanded and distribute x squared as a multiplier, because that will make the entire process of integration, which could be done in just a minute, to more than 5 minutes. Why? Because the process of expanding this is long and you need to multiply x squared if that is the case. So what you do, you choose the complicated, the more complicated expression of the two, and I think this one is the complicated expression, and you make that as your u. So you have x cubed minus 1. In this case, if that is your u, then if this is u raised to n, your n is equal to 4. Now, what is the du of this u? The du is 3x squared dx. Derivative of x cubed is 3x squared, negative 1 is 0. If you notice, you already have here the x squared and the dx. So what do you lack? You lack the 3. What you do, you make it complete. You multiply by 3 here and you divide by 3 before the integral. It's just like you're multiplying by 3 over 3. Why would you do that? Because you need a 3 in the derivative of this u raised to n. This is your u raised to n, and this is your du. And the 1/3 is just a constant that is written outside. You cannot simply multiply by 3 because that will alter the original integral. So there has to be 3 over 3. The 1/3 that you did not use will appear or will be written before the integral sign. So if you use power rule for u raised to 4, that would be 1/3 u raised to 5 over 5. And what is the u? You go back here. It's x cubed minus 1. And you just affix the 5 here. And you multiply the 3 over 5. Rather, the 3 and the 5 in the denominator. Do you get it? So substitution applied still to power rule. Any question? Okay, so let's proceed. So I will clear my drawings here. Now we go to the next one, the next slide. Now you have a radical sign multiplied to 5x. Okay, 5x. Now what will you do with this? You have 1 plus x squared multiplied to 5x. Actually, it's not a square root, but it's a cube root because you have 3 in here. Okay, somebody wrote in the chat box. Okay, I will check attendance later, okay? Now, if you choose the u as 1 minus x squared class, your n is 1/3, meaning this is your u raised to n. What's the derivative of 1 plus x squared? That's 2x dx, right? Derivative of x squared is 2x dx. 1 is 0. You already have the x here, but you don't need the 5. So what you do, you place the 5 outside, but you need to multiply by 2 over 2 because you need a 2 here. I place a 2 there. And of course, you place 1/2 outside. So this 5 and that 1/2 is here. 5 times 1/2. And your cube root of 1 plus x squared is your u raised to n, and this is the du. If you use power rule for 1 plus x squared raised to 1/3, your n will become 4/3, and the denominator will be 4/3 because we copy the resulting exponent of the u. This 5 times 1/2 is 5/2. Okay? This 4 and 3 will multiply with the 5/2 here. The 3 goes up the 4 in here, so that's 15 over 8. Your u is 1 plus x squared and your n, and rather, yes, your n is 4 over 3. So this is your final answer. Okay, still using power rule. Any questions? Okay, so there's none. So I hope you follow, you follow through. Okay, we have the last two examples here on substitution. Example number 7. The square root of 5x cubed plus 3x minus 8 multiplied to the quantity 5x squared plus 1. Never you see such expression, class, you always choose the more complicated expression as the u. Okay, this one is complicated than this. So if you set it as the u, this is then your u raised to 1/2, where your u is 5x cubed plus 3x minus 8. If you will differentiate this, that would be 15x squared plus 3, right? Because the 8 here will have a derivative of 0. The 15 and the 3 has the common factor 3, so it's factored. That leaves you with 5x squared plus 1 to be multiplied to 8 to make it equivalent to this one. Now, seeing this, you already have the 5x squared plus 1 quantity here. So you only need the 3. So I place the 3 here to complete the derivative of your u. And I place 1/3 before the integral. So that's the reason you see here a 3/3. So you have here 1/3 integral of this u raised to 1/2 because it's under the square root sign as this, and this entire thing is the du, and this is your u raised to n. So the exponent 1/2 will add 1 to it. It becomes 3/2, and your denominator will be 3/2. The 1/3 that you did not use in here is in here. So 1/3 u raised to 3/2 over 3/2. So the 2 goes up. The 3 and the 3 multiplied to each other. So 2/9. You copy the u, which is 5x cubed plus 3x minus 8 raised to 3/2 plus c. So that's your power rule with substitution. Any question? Okay, so we go to the last one. So we go to the last. Okay. Substitution, 8th example. Now, understanding the principle of substitution is very useful, class, whenever you're dealing with complex expressions. Like this one, you have a sine 3x over a cosine cube of 3x. You always look for association between functions that are written in your integral. We know that your cosine is related to the sine and vice versa because one is the derivative of another. If you will consider your cosine cube of 3x as your main function and it's raised to -3 because it has here 3 as the exponent, its derivative is negative sine 3x times 3 dx. That would be the case. Another one is you do regrouping as written here. Okay, regrouping in the sense that one of the cosine here goes with the sine and the cosine squared here is set aside. The sine over cosine is tangent 3x and 1 over cosine squared 3x is secant squared 3x. This is your u. This is rather your tangent u. And this is the derivative of the tangent. Okay? This is the derivative of the tangent specifically. I will erase this one. That way you will see that your original function is the tangent 3x. The derivative is the secant squared of 3x dx. Wait, plus, I cannot write. So I will have this entire thing as the u. So this is the du. This is your u raised to n. Now, if this is the du class, if tangent 3x is the u, and its exponent is 1, so you can use power rule, the derivative of tangent 3x plus is secant squared 3x plus the times the derivative of the 3x here, which is 3dx. You're using already chain rule in differentiation here. So it's 3 secant squared 3x dx. So you lack the 3 here. So that's the reason that you will multiply by 3 and place 1/3 before your integral. So you have here 3 over 3. So 1/3 tangent 3x, this is your u raised to n, and this is your du. So you can use power rule. Your n is 1, so it becomes 2. U raised to 2 over 2, this is your 1/3. And you just copy what is the u, and that's your tangent 3x. It's squared, so you also square it here, and you multiply the 3 and the 2 that appears in the denominator. That's one way of solving this problem. Okay? The other one is the one that I mentioned to you a while ago. You can write it as cosine 3x raised to negative 3, and this is your sine 3x dx. They're just the same, right? So this could be interpreted as u raised to n, and this is your du. What's the derivative of cosine 3x? It's negative sine 3x times 3 dx. So you need negative 3 in here, so you place here negative 1/3. Do you follow? So your cosine 3x has the derivative negative 3 sine 3x dx. That's the complete derivative using chain rule. So you introduce your negative 3, you should have negative 1/3 before your integral. If you use power rule to this, I will just write the answer here. It would be negative 1/3. You copy this one. If you use power rule to this, that would be cosine 3x raised to negative 2 over negative 2. Correct? Of course, the plus c is there. This is negative, negative, positive. 3 times 2, that would be 1/6. Cosine cube, or rather cosine 3x is, what is this? Secant squared 3x, right? So another way of getting the integral of this expression here is this one. 1/6 secant squared 3x plus c. Now, you may say, Miss Ali, hindi man na sila the same. Hindi sila the same. If you will see, they are not the same. But we know that secant squared 3x minus 1 is tangent squared 3x, right? You may say, Miss Ali, what about the negative 1? It's compensated here in the c. So if you will change the tangent here to secant, it would be this one. It would be secant squared 3x minus 1 in here. The constant minus 1 multiplied to 1/6 together with the c is still another c. It's an arbitrary constant of integration. So then, the two answers that we have, this one and this one, are both acceptable for this particular given integral. So either you use power rule for cosine cube 3x, or you use manipulation here. That way you will have the tangent and secant squared and still resort to power rule. You will still have the same answer. Or rather, you will have still the same answer after simplifying. Do you have any question? Or is there a part that you'd like to be clarified? Do you get it? No questions? Okay, so since there are no more questions, I will clear here the markings. You will have your 5-minute break. My time here is 3:53. You come back at 3:58. Okay? We will proceed with module 2. So let me share my screen to module number 2. Okay, I hope you can see the screen now. The first module is the concepts and formulas, the fundamental formulas of integration. So the very important concept of how to deal with the constants that appear with your functions, how to deal with several terms in your function, and the use of substitution, whether it's in power formula or in trigonometric functions. So that's the coverage of module 1. Now we proceed with module 2, and in here we're going to discuss more types of functions and their corresponding integrals. Okay, so for this module, we start with an integral yielding a natural logarithmic function. Or what is this expression in your integral that will give an answer that is the natural log, and that is the log to the base e, because we also have the common log, which is the log to the base 10. So ln is the natural log. So this is to be understood, class. I would like to emphasize that the derivative of the u that is written in the denominator is in the numerator. So it's du over u. Whenever you see this, the answer is the ln of u, whatever is this u in the denominator. One way of checking this one is you perform differentiation to your answer here. So what is the derivative of ln u? As you have learned last semester, the derivative of your ln u is du over u. So that is why we say that integration and differentiation are two inverses or two inverse functions of each other. So that's it. Now, if you're going to apply du over u in here, the first thing that you have to do is recall that primary concept about the constant. So in here, your constant is 1/3. You write it before your integral, leaving you with the dx over x. What's the dx over x? That's the ln of x. Because the derivative of your x here in the denominator is in the numerator. So your answer is ln of x. Now in example 2, you don't have a very simple u, but rather this time it's x squared minus 1. Okay? If that is your u, if you differentiate it, the answer is 2x dx. But what you see in the numerator is only x dx. So to complete the du of your u, you write here 2 and you place here 1/2. So it's the same as multiplying by 2 over 2. You only need the 2, so the 1/2 stays before your integral. So you have 1/2 2x dx over x squared plus 1, which gives you 1/2 ln of u. What's the u? That's x squared minus 1 plus c. Do you follow? Any question? Okay, so very simple, miss. So we proceed. So we go to the second set of examples. Now, in here, you notice that the degree of the numerator is greater than the degree of the variable in the denominator. What do I mean with degree, class? It's the exponent, the highest exponent to which your variable is raised to. So this one is squared, this one is 1. So what does your differential calculus or even your algebra tell you? Before you even check whether you can use the formula of the natural logarithmic functions, meaning an integral, before you check whether you will have an integral that will yield a natural logarithmic function, if the degree of the numerator is higher or equal to the degree of the denominator, divide first. So what we did here is divide x or distribute x as a divisor to x squared plus 1. If you do that in here, you will have an x. If you do that in here, you have 1 over x. Then process this integral term by term. So the integral of x using power rule is x squared over 2. The integral of dx over x is ln of x plus c. I think this is very simple. The one in which the degree of the numerator and the denominator is equal is illustrated here in example 4. So your numerator is degree 1, your denominator is degree 1. So you have to resort to long division. What is long division? So you just have to do division the way you do it when you were in the elementary. So your x plus 1 will be divided by x minus 1. Arrange your variable here, which is to be divided by this variable here from the variable having the highest exponent down. So meaning it's decreasing in exponent. The same thing here with the divisor. Then divide. So x, this x here divided by this x here is just 1. You don't look at the next variables. You just need to refer to the first term. So if you multiply this 1 by x minus 1, you have x minus 1. Then subtract. So this will be 2. This 2 is remainder. So this you see here a 2 over x minus 1. Because the way we write a remainder is we divide it by the divisor. This one is this one here. Then you just process the integral. So this one will give you an x at dx. So if you distribute actually, you will have something like integral of dx for this. And the other one is 2 integral of dx over x minus 1. If your u here is x minus 1, the du is just dx. So it's in here already. So if you get the integral of this, it's x. If you get the integral of this, that's ln of quantity x minus 1. You have a constant 2 in here, so that should be multiplied, but that's a constant. Do you follow? So ln. So our example, starting from example 1 to 4 here, yielded a natural logarithmic function because of the du over u. Now we proceed with more examples here. Interrupt me if you cannot follow. So we have here number 5. So look, we have a polynomial here in the denominator, second degree. The numerator is just first degree. So there's no need for you to divide because this one is lesser in degree as this. So you just check. So since the denominator is longer than the numerator and is of degree higher than the numerator, you can try. So when you integrate class, and if you're still a newbie in integration, you always try. When that particular procedure or technique you use won't work, then you go to the next. It's not class, shall I say, you are just being normal if you're just trying at the start, because we always start somewhere. So we learn as we go along. So you just try if whether this one will yield an ln. So if you have in mind that I'll try, this will yield an ln, then you will set a u, which is equal to x squared plus 6x plus 5. Why will you set this as the u? Because the form of the ln you answer for the integral is du over u. So this must be your u. If this is your u, what's the du? So the du of that u is 2x plus 6. The 2 and the 6 having 2 as the common factor, so that would be x plus 3. So right away, you will recognize that the x plus 3 dx is in here already. You need only to multiply it by 2. So you multiply by 2 here and you place 1/2 before your integral. So equivalent to multiplying by 2 over 2. So it's in the form actually of 1/2 du over u already, if it's written like this. So 1/2 ln of u, 1/2 ln of x squared plus 6x plus 5, because that's your u. Okay? Do you get it? Okay, no reaction, so we go to number 6. Okay, number 6. This is the 6th example, and this time we're dealing with a trigonometric function, a tangent function. Recall the basic functions, the 6 trigonometric functions that can be directly integrated. We only have the sine, the cosine, the secant squared, the negative cosecant squared, the secant u tangent u, and the negative cosecant squared u. And again, negative cosecant u cotangent u. This one is not included there. So you have to think of its equivalent identity. What is its equivalent identity? It's the sine x over cosine x. The way it's written now, I could see that one is the derivative of another. But again, if I wish to try if du over u will work, then my u will be my cosine, and the du will be, of course, negative sine x dx. I lack only negative 1 here. So that requires us to multiply by negative 1 over 1. So it is actually the negative of du over u, where u is cosine x and du is negative sine x dx. So the answer then is negative ln of the u, which is cosine x. Okay, we go to the next slide. Just write on the chat box or interrupt if you have any question. What about this time, this one? So we're now increasing the complexity of the example. Here you have a cotangent x in the numerator, and look at the denominator. It's ln of the cosecant of x. The argument of your ln is a cosecant function. So it's not the usual ln x, ln of x plus 1, x squared minus 1, but rather the argument of your ln is another function, which is a cosecant. But still, if you wish to try if this will conform to the form du over u, then this entire ln of x will be your u. Here it is. If you differentiate ln, it's du over u. This is ln of u. The derivative is du over u. In here, we're talking about a different u in the ln of cosecant x. Our u here is the cosecant function. So if we need to get, so this one will have a derivative of du over u, I need to differentiate the cosecant x. What is its derivative? It's negative cosecant x cotangent x dx. What is the u? Since ln of u is du over u, it's cosecant x. That is if my ln of u in the original function is the ln of cosecant x. If it's differentiated, it would be like this. You could see that the cosecant gets cancelled, so you are left with negative cotangent x dx. And you have already the cotangent x dx here. It needs only the negative 1 here, and you place here negative 1. So if we will properly write this one now, it would be something like this. So you have here the negative 1 over 1 already. And this is now the way I write it is negative integral of your u, which is ln of cosecant x, and its du, which is negative cotangent x dx. So this is du over u. So if it's du over u, then anong answer gani sa du over u? It's the ln of this u. So it's the ln of the u, which is another ln. Ln of cosecant x. The negative sign in here appears before the ln. So it's possible that you will have an ln of an ln cosecant x. The du of the main function ln here, or rather the u of the main function ln here is ln cosecant x. The u of this one is cosecant x. Okay? Now, before I go to number 8, do you have any question? Do you follow the process? Or reaction? So I will just proceed, class, if there aren't any reactions, if there are no clarifications, okay? Now, we go to number 8. 1 over the square root of x times 1 plus square root of x. Looking at it, as a student, you will get easily overwhelmed. Ano ni siya? Kadamo, nasa square root of x. What you're going to do is choose the most complicated group of terms or functions to make as your basic function. Make it as your basic function. In this case, class, this is 1 plus square root of x. That was chosen to be the main function. Okay? It's the main function. Now, Miss Ali, what will we do with the dx over the square root of x here? Leave it for now. If you're just trying, if a particular formula will work, you will try to check whether the u that you will assign to this one will yield a du that will be conforming to the remaining function that you have. This is your remaining function. Okay? If this is your u, the du of this will yield a 0 or 1 because it's a constant. And the derivative of square root of x using power rule is 1/2 x raised to negative 1/2. 1/2 x raised to negative 1/2. And this is it. Okay? So you see, the function which you did not consider as your main function, the group of terms rather, which you did not consider as your main function, will stand as the derivative of your chosen u. Okay, it's the derivative of this 1 plus square root of x. So what we'll do, since you only lack 1/2, you only lack 1/2 here because you already have the dx over square root of x, you place 2 here and you place 2 outside. That's the reason why you have multiplied by 2 over 2. So you see this 2 in here, and this is your u. If it's properly written, class, that way it's clear for you. It's 2 dx over 2 square root of x over 1 plus square root of x. This one is this, comparable to du over u, which will yield an ln of this u, this one. So it's 2 ln of 1 plus square root of x, because this is your u, plus c. Do you follow? Is there a part that you'd like to repeat? Do you follow the process? Or can you follow the process? Okay. Sige. So I will proceed if there aren't any comments or clarification. The next function here, so we're done with natural logarithmic functions. Integral, yielding, logarithmic functions, or the ln functions. What about the natural exponential function? So this is now the third type of function that was given to you. The first, we have the trigonometric. The second is the natural log. And this is the third, the natural exponential function. How will you interpret this one? How will you interpret? You have an exponential function with an argument equal to u. It should be multiplied to the derivative of this u. And the answer is the original function, e raised to u. How will I interpret this? As long as the provided exponential function is multiplied to the derivative of its argument, I'm referring to its exponent, the answer is the exponential function itself. So eu du has the integral equal to eu, or e raised to u, plus c. Now, if we'll apply it in this simple example, e raised to 2x dx. Your u being 2x, the derivative of that is 2 dx. So what do we lack? We only lack that 2 in here, and we place 1/2 outside. So what you don't need is the 1/2. So it's the constant written before your integral. You need the 2 to complete the du of this u. So the answer is this function itself, e raised to 2x, and don't forget the 1/2, the constant 1/2, which was set aside. Question? Okay, I'll proceed then. So I will clear my markings here. We'll proceed. Now, I will make this bigger. Now, you can see you have an exponential function here, and it's multiplied to x squared minus 1. Whenever you have this particular combination class, always choose as the main function the exponential function, because you can try to make the remaining expression, which is purely algebraic in the variable x, as its derivative for the u. What happened here is this is assumed to be an EU du integral. So that's the assumption, the original assumption. So if it's an EU du integral, the u is the exponent of the e, or the argument of the e. It's x cubed minus 3x plus 1. How do you differentiate this? This is 3x squared minus 3. 3 is common, so it's factorable. So it's 3 times the quantity x squared minus 1. So see, this algebraic expression that was multiplied together with this exponential function is actually the derivative of its argument. It only lacks the 3. And you need, of course, 1/3 here. So that would be 1/3 EU. So 1/3 EU. Why? Because this is your EU and this is the du. EU du, the integral of e raised to u du is e raised to u. Right? So just complete the derivative of the u. Actually, it's the same principle that was applied in ln in an integral yielding an ln function. It has to be du over u. The derivative of the u has to be in the numerator, the u in the denominator, in the case of the ln. So the same thing in here. The du of this u has to be complete. Now, I will proceed. What about this? Can this get any simpler, Miss Ali? The answer is no. So that's the reason why you really have to be good in your differentiation, because integral is extra challenging compared to differential calculus. Now, you have an exponential function under the radical sign, and you have an outer exponential function here. So question, which will be your main function? I gave you already a suggestion. The main function is always the more complicated of the two. So meaning, this is your main function. You set this as the u. So this would be now your u raised to n. Okay, you may say, Miss Ali, I thought we're thinking of an integral that will be yielding an exponential function. It's not always like that. It could be that with the concept of the exponential function, you will use it together with another formula. So in this case, this would be your u raised to n, and you can check whether this is the derivative of this u here. That way you can use power rule. Your n here is 1/2. Your u is 1 minus e raised to x. If this is your u, then the derivative of this u is negative e raised to x dx. So you see the remaining function that you have here on the left, and this differential of x is actually the derivative of your u, this u in here. What do you lack? You only lack the -1. So this is an integral that does not yield an exponential function, but is still using the concept of the exponential function because you need the derivative of this u here. So you have the negative of the integral of u raised to n, and this is its du. This is the du. Ini silang duha. O, isa na sila as the du. So if this is u raised to n, then you need to use power rule for the 1/2. So that will make it 3 halves. The denominator is 3 halves, and you have here the negative sign. So negative, these 3 halves become 2/3 because in here it's in the denominator. Your u is 1 minus e raised to x raised to 3 halves. So this is an integral that is dealing with an exponential function, a natural exponential function. It's not yielding a natural exponential function, but it deals with it. Okay? I'd like to end with slide number 9. I will continue with the next one on Thursday. Okay, any question in here before I go to the last? Okay, I will clear my markings here first, then we'll go to the last slide. Okay, this one has 2 examples. You have e raised to tangent of x, secant squared of x dx. So your exponential function cos in here has the argument which is tangent of x. So this is not the usual e raised to x or e raised to u. No. The argument of your exponential function is a trigonometric function. Whenever you see such class, hindi magkulba, tanawa lang maayo. If this is your e raised to u, the u here is tangent of x. What is its derivative? It's secant squared of x dx. So it's in here. So then the answer is this one, e raised to u. So e tangent of x plus c. Why? Because the secant squared of x dx here will serve as the derivative of your u in the exponential function. This principle is also applied in here. But this one will not yield an exponential function. Your main function here is the cosine of u. So you will apply here the concept of the integral of the cosine of u du. So your u here for the cosine function is the e raised to negative x. O e raised to negative x is the u. What is the derivative of this? It should be complete. The derivative of the u of your cosine should be multiplied to it so that you can have the integral of cosine of u, which is sine u. So let's check. What's the derivative of e raised to minus x, which is the u of your cosine? That's negative e raised to minus x dx. Derivative of e raised to u is e raised to u du. Ari naman ng iya nga u, which is negative 1. So you have negative e raised to minus x dx. So see, this thing, the e raised to negative x and this dx here, sorry, is actually your du. It only lacks the negative 1. So again, you place here the negative 1. If I will properly write it, it's negative integral of the main function is cosine e raised to negative x. Its derivative is negative e raised to minus x dx. So your main function is the form cosine of u, and this is the du. So the answer is sine. The sign of the u, the sign of e raised to minus x. You just affix this negative sign which was written before your integral. That's for the natural exponential function. We will deal with the general exponential function on Thursday class. Based on the topics that we have discussed so far, do you have any questions? Okay, so I have written your problem set already. Please work on it. Work on it that way. On Thursday, I will give you the remaining time to work on it so you can comply with the submission. So you need to know this one, that way you can submit the 2 problem sets related to this module. Okay, I'll stop sharing now.